Thank you very much for the introduction. It's a great honor to be able to present here. Hi, my name is Beom Heyn Kim, or simply call me Ben. And this work was done with Professor David Lee at the University of Toronto. So I would like to talk about the Caelus, which is a system for verifying the consistency of cloud storage services with the battery-powered devices. So these days, we have a variety of cloud storage services. These are managed by the third parties, so their customers are concerned about their information security. So as bread and butter, encryption can protect data confidentiality, and digital signature can protect data integrity. However, these are not sufficient to protect from the consistency attacks. As one example of consistency attacks is a classic fork attack. Let's assume there is a Git repository service hosted on the cloud, and client A has pushed initial update to the cloud, and which is visible by every other client. Now, malicious cloud starts omitting any update from client A and C and hide them from client B, and vice versa. Now, any subsequent updates made by client A and C will not be seen by client B. Client B's subsequent updates will not be seen by client A and C either. So now the view of history of operations is forked into two. As fork sustains longer, recovering from the attack by merging conflicting changes will be getting more and more difficult. So detecting the consistency attack in timely manner is important. And in this example, the updates are omitted, but the attack can be easily extended to reorder, replay, and delay. And Caelus tries to catch this kind of consistency attacks with the battery-powered devices in a battery-friendly and timely manner. There have been several related works trying to detect the consistency attack. And here's a table summarizing them. The first column of the table means the solution is battery efficient. And the second column means the solution can support timely detection. And the last column means the solution can support various consistency models, such as eventual, causal, and strong. Normally, battery efficient solutions do not require their clients to exchange views periodically. So clients can sleep most of the time, and therefore they're battery efficient. However, without exchanging views periodically, it is hard to enforce the timely detection. On the other hand, the solutions supporting timely detection require their clients to be up and running all the time to exchange the views periodically over the direct trusted client-to-client communication channels. So their clients need to be awake all the time, and therefore they are not battery efficient. So Thunder BFD2F and CloudProof are battery efficient, but cannot support timely detection. On the other hand, Depot Spork Venus can support timely detection, but they're not battery efficient. And none of these actually support the various consistency models, either strong or just causal. However, different consistency models are useful in different contexts. For example, weak consistency model is better for scalability, lower latency, and favoring in availability in failure scenarios at the sacrifice of consistency, which can be useful properties in certain contexts, such as shopping cart example. And therefore, it is important to support various consistency models. So Caelus tries to achieve all these three properties. So Caelus does not require direct trusted client-to-client communication. It is battery friendly. It can support timely detection. At last, it can also support various consistency models. So here's the system overview. So we have a bunch of battery-powered devices as a clients, which we trust, and we untrust the cloud. We have a special client called Attestor, which fetches client operations from the cloud and signs it to generate the attestation. Then a tester posts the attestation on the cloud so that other clients can download it from the cloud. With the attestation, client can perform consistency verification procedure by comparing their own local view with the attestation. As we discussed, malicious cloud may mount consistency attack and provide different views to the different clients. Providing a single view will allow us to detect consistency attack and solve the issue. So a tester fetches operation history, attaches sequence number and timestamp and sign them to generate the attestation. Now this attestation will serve as a single view that will be distributed to the client through the cloud, so that it allows us to detect the consistency attack. With the sequence number, a malicious cloud cannot omit, reorder, or replay the attestation. And the timestamp allows clients to check whether the attestation is delayed or the new one. And the signature prevents from the tampering attack. And same technique is used to protect each of the client operation as well. Now, since we assume there's no direct trusted client-to-client communication channel, every message is going through the cloud, and which means malicious cloud may block the communication by dropping every message. So in this example, client B and attester cannot communicate through the cloud. Therefore, client B will have no idea whether there was a new attestation to receive or not. So we devised the scheduled attestation where every client expects to see the attestation at the scheduled period. So in this example, if client B does not see the attestation at the expected time, it will notice it and raise the flag. With the scheduled attestation, we can enforce the timely detection. But we have to consider two timing factors. First, when client sends their operation to the cloud, it will take some time for the operations to be fully replicated across the distributed nodes in the cloud system so that every other client can see those operations. And we account this timing factor as visibility time, or TS. And at attester, generate the scheduled attestation periodically at every attestation period, or TA. Attester sends this attestation to the client through the cloud, so there is some network and processing delay involved, but we will just focus on TS and TA for this talk. In short, Caelus enforce the time-bound TS plus TA for operation to be verified. Now let's look at the consistency verification procedure through the strong consistency example. Suppose there is a couple of clients making operations colored in blue and red as they're described in the ground truth box as they appeared in real time. A tester comes along, fetches the operation history, and generates the attestation as we discussed earlier. Now, since malicious cloud may have tampered with the attestation, the first thing client has to do when it receives the attestation from the cloud is validating the signature of the attestation. Also, it has to check sequence number and timestamp as we discussed. The next step is presence check. So every client is responsible to remember its own operations and verify them. And note that malicious cloud may have reordered, replayed, omitted, or tempered some of the client operations before it gives the operation history to the attester. So the client first has to validate signature on each operation. So in this example, client B can detect there was tampering attack by trying to validate the second operation's signature. Now client also has to check sequence number, and client A, in this example, can figure out there was some omission attack by figuring out there was sequence number 2 missing. The last step is consistency model specific check. And here's an example where get reads the stale value. And in strong consistency, every get should read the value from the immediately preceding put in the history. So client A's second operation and client B's first operations can be verified because they actually read the value from the immediately preceding put in the history. However, when client A tries to verify its third operation, it noticed that there was more recent put in the history. So the client A can detect that its third operation has read the stale value. Caelus not only support a strong consistency, but also support the weaker consistency models such as eventual and causal with a certain time bound. And eventual consistency model requires additional checks due to visibility time that is greater than 0, which allow clients to read the value from a put older than the immediately preceding put in the history, which means there can be more than one put that get possibly read the value from. So that makes check a bit more complicated than the strong consistency model. And it is similar for causal consistency, but it additionally requires vector clocks to keep track of the causal ordering between operations. Further details are discussed in the paper. So to provide the timely detection, a tester should generate the scheduled attestation in short period. But this will keep the tester awake and therefore will deplete the battery on the attestor device quite quickly. To solve this issue, we devised the Attestor-Partitioning scheme where we split a tester into two, root attester and the active attester. So root attester selects an active attester device at every RA period. And active attester generates the actual scheduled attestation at much shorter attestation period. And note that RA period is much longer, and RA needs to wake up only when it has to select active attester device. Most of the other time, it can sleep, so we can save a lot of battery consumption on the RA device. And when we select active attester device, we select a device that's already awake for other purposes, like being actively used by the users or running some background tasks like a software update. So we can minimize the additional battery increase on the AA device due to short periodic scheduled attestation. After RA period is over, AA stops, and RA either renews the new old AA or selects a new AA device. But it is important to note that AA stops after RA period is over, and RA only selects only one active attester for a given RA period. Otherwise, malicious cloud may trick the clients to have more than one active attester. Therefore, it can effectively fork the views. We also did some measurement study with Amazon S3, trying to see whether Caelus can effectively catch its consistency violation. But we don't mean that Amazon is trying to trick their customers. S3 actually provide eventual consistency models without publishing any visibility time. But using a shorter visibility time than S3 can support, actually allow us to effectively simulate a malicious cloud provider. We try to write non-repeating value to the same key from the East Coast server with timestamp embedded in the value, and try to read from the West Coast server and try to get the timestamp. Then based on this timestamp, we can calculate how long it takes for the operation to be replicated from east to the west. So with this, we can get ground truth whether operation has violated visibility time or even the time bound we enforce. So we fixed the attestation period and varied the visibility time by decreasing it. So let's look at what's happening in the timeline. Suppose we made the put operation writing value 15 to the key x. It will take at maximum TS time for the operations to be fully replicated. And it will take at maximum TS plus TA time for the operations to be fully replicated, attested, so that clients can verify it. If the operation takes longer than TS, then we label it and group it as a GT service group. where GT means ground truth. And if it takes even longer than TS plus TA, which is a time bound, we label it and group it as a GT Caelus group. And every operation belong to GT Caelus is also belong to GT service. And what Caelus tries to catch is every operations belong to GT Caelus that is violating the time bound, and some of the GT service those operations that those operations in the GT service, but not in the GT Caelus, with some probability, because the attestation timing is time affects the catch. So those operations caught by the Caelus are labeled and grouped in the violations group. Now let's look at the resulting table graph. And the column of the graph shows the percentage of the gets belong to each group. And the row of the graph shows the variations in the visibility time. And as you can see, the blue line representing the violations group is always above the red line representing the GT Caelus group, which means Caelus have caught every operation violating the time-bound TS plus TA. And you can notice there's some gap between those two lines, which means Caelus could have caught some of the operations belong to GT service only, but not in the GT Caelus. And we could have tried to catch every operations violating the visibility time by trying to get TA infinitely close to the 0. But this is infeasible in real world, because that means a tester should generate the scheduled attestation at the infinitely fast pace. We also did some battery consumption measurement study, and when we measured the idle phone's battery consumption, the phone was sleeping most of the time. And then we also measured the battery consumption with the single attester running on the phone, where phone generates the scheduled attestation in short period. Here we disabled the Attestor-Partitioning scheme. So phone was not asleep. Phone was never in sleep, and therefore battery consumption was increased significantly. With the Attestor-Partitioning scheme enabled, we placed a root attester on the phones, and therefore phone could sleep most of the time, and the additional battery increase was minimized. So in short, Attestor-Partitioning can save about 40 times of additional battery increase compared to single attester. In conclusion, Caelus is able to avoid direct client-to-client communication and use untrusted cloud to deliver messages securely. The role of the tester can be partitioned to achieve battery efficiency in a secure and timely manner. And Caelus can support various consistency models, and at last, evaluation shows that Caelus is effective, battery-friendly, and efficient in terms of CPU and network cost. Thank you very much. And I'll happy to take any question.
Okay, questions?
Hello, Cami Vanier, Indiana University. So you mentioned that you're trying to select devices that are already on for doing attestation, so that way that you're doubling up on when the user is using them. Users typically only use devices for about 45 seconds on average, though they use them frequently during the day. How are you figuring out which of the devices in your set are going to be on and at what points in time? Because they don't stay on for very long.
Right, I think that actually requires more rigorous user study than we did. And what we just think as a solution to that, it was like doing some profiling and see the user's pattern of the device usage, right? So that we can kind of prioritize which device will be likely up for the next, I don't know, a few minutes or so that we can pick that device first, yes.
Thank you.
Okay, let's thank the speaker again.